This title, The Real Number Set, has a lot of meaning to it, even though it seems very straightforward. The first part, this real word, seems odd, that we would have to say that a number is real. But believe me, when you get to Algebra 2, there's a whole other group of numbers that are imaginary, but we will save that for Algebra 2. But it's important at this point that you start to use that word, the real number set. This number set also is vocabulary intensive. It just means a grouping of items, and in this case we're grouping numbers together and we give them a name. The most basic number set that you learned when you were in kindergarten were the natural numbers, or sometimes they're called the counting numbers. That might be an A in there, but I'm just not a good speller. Those natural numbers are numbers that you would count on your fingers, and so you would say 1, 2, 3, 4 when you were a little kid and count those numbers. And those are the natural or counting numbers. But then there's another number set that is larger than the natural numbers, but not very much larger. It's called the whole number set. And all that does is it adds the number 0 to the natural numbers. So when you count out the whole number set, you would start with 0, 1, 2, 3, 4. And to keep those straight, I always think of this O in the number, or the word whole as my 0 to help me remember. Well, that whole number set became part of a larger number set when you got into middle school and started talking about those negative numbers. And the negative numbers are called, when you include the negative numbers with your whole numbers, become the integers. And so I will write integers here. Now the integers include the whole numbers still, that 0, 1, 2, 3, 4, but now we're also talking about negative numbers. -2, -4, -3, etc. So maybe you notice there's a whole group of numbers that you're used to working with that aren't here. And those are the decimals, or maybe even the fractions, depending how you look at it. And so when you are in the integer number set and zoom out with your lens to an even larger number set that includes all the ones you see there, we call those the rational numbers. I'm just going to use the symbol. Now notice rational numbers has the word ratio in it. That helps me remember what's in here too. Ratio you can think of as that fraction we were talking about. So 3/4, that fraction is a rational number. But if we wrote it as a decimal, it would be written as 0.75 or 0.75, 75 cents, however you want to think about it. And so there are other fractions that when you divide them, you end up with decimals that end. And that's an important thing to notice. There are other fractions in here that end up with decimals that don't end, but rather they repeat. So for example, 2/3, if you made that a decimal, it would be 0.6 repeating. And so to remember those rational sets in terms of decimals, you can say the decimals end or repeat. And that's an important concept to help you remember. Alright, on the right-hand side of this diagram are another set of numbers that have nothing to do with the rational numbers or those sets inside the rational number set. And those are called, well, the opposite of rational, they are called the irrational numbers. And if you're good at English, you know that IRR means not. So irrational means not rational or cannot be written as a fraction of two numbers. An example of an irrational number would be the number pi. Now there's the symbol for pi, but we know that it represents that decimal that never ends and doesn't repeat. And so pi is considered an irrational number. If you took the square root of 10 on your calculator, you're going to get a decimal that does not end or repeat. That number is 3.162277, and it keeps going on forever too. A lot of square roots will turn out to be irrational numbers, except for the square roots that end up in whole numbers. So if I took the square root of 25, that would belong over here because that's the number 5. In fact, you could put that up into the whole number set. But other numbers that are not perfect squares, like the square root of 2 or the square root of 3, those would be irrational numbers. And so when we're talking about decimal versions, it's nice to say, or remember in this case, that irrational decimals, they don't end and they don't repeat. And so keep this chart handy because you might refer back to it quite a bit. And this is actually really important foundation for the rest of the math that you'll be taking. So this brings us to our number line. And I'm just going to put some numbers on our number line. If you ever have a number line that's blank, just go ahead and put whatever numbers that you need on it. I'm going to go by ones. So I will include, I'm talking and writing, it's never a good thing, the negatives. And so if you were looking at your number sets on this number line, your counting numbers or natural numbers would be that 1, 2, 3, 4, 5, and not in between because those are a different number set. If you're talking about your whole numbers, all you would do is include that number 0. When you move over to the integer number set, those include these because now your negatives are included. And then if you were talking about your rational numbers, well, that would be like a whole line because all these decimals inside of there would be included. So here we would call this our real number line because it's made up of all real numbers. And it's important to know the relationship of numbers on your real number line. You need to know which ones are bigger and which ones are smaller. The further to the left that you move, the smaller that number is in comparisons to all the ones that are to the right of it. And so when you look at example A and it says -6, -10, and 5, you need to understand that -10 is the smallest number in that list, then -6, and then a +5. So when you're in the negative realm, you need to kind of flip your brain and think backwards. In this case, -5 is the smallest number, then -3, and then -2. So it's weird to say that a -2 is the largest number, maybe, for you in that situation. Letter C is giving us fractions, and in order to compare those on a number line, I suggest you make them decimals. Unless you're real good with converting fractions and getting that common denominator, go ahead and do that. But 2/3 I know is that 0.6 repeating, and then go to your calculator and you would do 5 divided by 8, and that answer is 0.625. And those were positive, and then -2. So the smallest number in this list is -2, and then you need to look at these two numbers, which in the 10th place look identical. You both have 6s, but then you need to move one spot over into your 100th place and compare those numbers. And this 6 and that 2 makes this the larger number of those two numbers, and so this one is considered smaller, or actually don't write it as the decimal version. The book and any test you take is going to want you to write it back as its fraction version. So 5/8 would come next, and then 2/3 would come. Alright, so letter D, same thing. I'll just convert these into, well, they're the same thing. So this is 0.625 again, but it's negative, so watch out for that. This is -0.6 repeating, and then 1 divided by 12 is 0.083, so we'll just say 0.08. And that one's positive. Alright, so the smallest number on this list now is going to be that -0.6 repeating. So -2/3 is actually our smallest number, and then -5/8 would be our second smallest number because it's further right, and then farthest to the right is our positive number of 1/12. Alright, you try this one, pause the video, and come back. And here's that final answer. Again, with all the negatives, you're kind of thinking in reverse. If you ever have trouble with this too, you can plot them on a number line, and that will help you as well. And earlier we were talking about how comparing numbers was really important, and we just did that when we ordered them, but we can use these inequality symbols to help us compare numbers as well. And so we will write down the definitions of each of these symbols. And the first one, I know sometimes it's hard to know which one that is. That happens to be the greater than symbol. I try to remember that. I like to think of reading left to right, and as I'm reading from left to right, I hit the greater side first. That's how I remember it. So this opening is greater than that one. If you look at the second one, reading from left to right, this side is open less than that one. You can come up with whatever tricks work for you, but let's write these down. And there are those. Go ahead and pause the video if you need a chance to catch up on that. This last one I included because you see it just enough to bug you. If you have an equal sign with that slash through it, it just means not equal to. So when comparing numbers down at the bottom, you're supposed to use the symbol that decides which one is greater than or less than. I like to go back to the old alligator eats the larger number. It works so well. So looking at number 1, the larger number is the 5, and so you would say that 5 is greater than a negative 8. Number 2, you have a negative 8 and a negative 25. Your larger number there is actually the negative 8. Negative 8 is greater than a negative 25, or you could read it in reverse if that helps you, that a negative 25 is less than negative 8. Next we have fractions again, and 1/2 is 0.5 is a fraction, or maybe you're thinking of money, that this might be 3/4. So the larger number is 3/4. You'd rather have 3/4 or 75 cents. Then we have negative 3/8 and negative 5/12. Using your calculator, 3/8 gives you 0.375, and 5/12 is 0.416, and these are both negative, and so you got to be careful there. And so if you were thinking of your number line, the one that will be the smallest is the one that is plotted most left on your number line, if that makes sense. You can sketch a picture. So if I was doing a number line, that 0.14 would have to go further to the left than my negative 0.3. And so the alligator, again, is going to eat the larger number, and in this case it's the negative 3/8.